All right. We have some fun stuff to do together today, y'all. But we're going to start with a dynamic programming problem. So I want you to take a few minutes and talk to the people around you and see if you can come up with any possible solution to this problem. And just to remind you, remember that dynamic programming is an algorithm optimization technique where when you have a problem that runs very inefficiently, recursively, that you can instead figure out how you save the work from sub-problems and then bring all of those solutions together to the final problem. So take a few minutes, talk through this problem. Out of interest, has anyone here ever heard of this problem? It's like a really famous computer science problem. Yeah, this is one of those problems that like computer scientists won't shut up about. And so I'm honored to maybe introduce it to you. But this is called the Knapsack Problem. Read through it, talk to the people around you, see if you can come up with just the straight recursive solution, and then see if you can find out how perhaps memoizing, i.e. storing results as you build them up, might optimize your solution. Go ahead, take like 2 full minutes to talk about this, because you should try to see if you can do some dynamic programming. Go ahead. Let me make a pull everywhere live. Also, I just made the pull everywhere live. Based on the rate of conversation slowing down, I am going to guess we didn't get too far on this item, and that is A-OK. So I'm going to talk through the recursive solution first, and then we'll talk about optimizing with dynamic programming. But before we even talk about any solutions, do we have any questions about what this question is asking? Any questions about this prompt? For example, anything you would maybe clarify if this was asked of you in an interview? Anything? Yes?
Are all weights and prices positive?
Ooh, great question. Are all weights and prices positive? For our situation right now, we are going to say yes. Yes. So just so that you can kind of understand what's going on, the idea of the knapsack problem is that we have a bag, a container, a knapsack, if you will, and that knapsack has a certain capacity. You can hold so much weight. And then you have a collection of items you might choose to put into that knapsack. And each item has an associated value, meaning like how much money it's worth, and an associated weight. How much is it going to take away from the capacity of the knapsack? And the goal is to find the combination of items that will fit in the backpack within its capacity, but that maximizes the total value of the items you've placed in the backpack. Any questions about what I'm asking to happen here? Okay. So this problem is what we call a decision problem. And I think I also realized I'm teaching 2 classes and I did dynamic programming in both, and I cannot remember to whom I said what. So did I say in this class that maybe your intuition should go off if you think recursive backtracking? Was that the other class? Crap. Okay, so if you remember from 143, we talked about an algorithm design tactic called recursive backtracking. It was part of the 8 Queens assignment. And the idea of something called recursive backtracking was if you're trying to find a solution to a organization and orientation in which there's sort of like a finite number of options, one of the brute force tactics for finding that solution is to sort of just like try every permutation. So you make a choice, then you recurse with that choice and see if that was effective. And then you have another sort of undo that choice after the recursive call. And the way that recursive backtracking goes is that it sort of just like tests all permutations of choices. That's why it was applied to the 8 Queens, which is a chess problem. And the choices you were making is like trying to place 8 queens on a board without them being able to kill each other. So you would like place a queen, recurse with that choice, place another queen, recurse with that choice, so on and so forth. But if you remember from 143, recursive backtracking was like, it's like super inefficient. And in fact, today, I hope that I will convince you that exponential time, meaning some number to the n, like 2 to the n, is so inefficient that in actuality, computers today don't even exist that can run a program that runs in that time and any type of scale. And in fact, this problem falls into one of those categories. And I bring up the recursive backtracking thing because a lot of times whenever you have a decision problem, that's the term we use for these organizational problems where the idea is like, okay, like I make a choice and then I try something else and like the eventual solution is a series of choices. So in the knapsack problem, your series of choices would be selecting an item, seeing how it fits in the backpack, and then trying every other permutation of items in combination with that, and eventually finding which is the like highest value combination of items that still fits in the backpack. And so any type of problem that is like that is just well set up for a dynamic programming optimization. So this is also me trying to give you an example of when you might want to use dynamic programming, if your brain goes to recursive backtracking, or if your brain goes to like, well, at the very least, I could just try every combination and pick the best. Chances are you might be able to do something better with memoization from dynamic programming. Does anybody have any ideas so far? Anybody have any interesting conversations about how we would go about implementing this just recursively, not optimally whatsoever, just from a recursive standpoint? Any ideas? Let's see. Yeah.
You can start with one and say, okay, is the stuff that I have inside there exceed the capacity?
Mm-hmm.
If no, then you look at the other objects and say, okay, if I add this, it will exceed the capacity.
and that's pretty foundationally what we're trying to do. Again, it's about permutation. So what we're going to do is we're going to place an object into the backpack, remove that object's weight from the capacity of the backpack, check like, hey, does this thing fit? If it does, make another choice, add another item into the backpack, and then try every combination. And actually the combinations we're going to do is we're going to loop over a set of items, and at each item we're going to actually trigger 2 separate recursive calls. One recursive call that will reflect us having selected to add that item into the backpack, and one recursive call where we don't add that item into the backpack. So it's sort of like at each recursive level, we're looking at each item and we're making the choice, yes, it's in, or no, it's not. That's actually where the 0 and 1 in the name of this problem comes from. People call it the knapsack problem, or sometimes people call it the 0-1 knapsack problem, because the idea is that you're doing this sort of decision algorithm where try it with this thing in, try it with this thing out, and recurse. So let's take a look. Here is some code for a solution to this. So we have some parameters here. We've got an int n, which will keep track of which item we are currently considering. And that int value will reflect the indice in the array that represents that item. And then we take in 2 arrays, one called W and one called V. W has all the weights of the items, and V has all the values of the items. And so n, let's say if n was 0, then to get the weight of the item, I would pull 0 of W. To get the value of the item, I would call 0 of V. I also am taking in the capacity of the knapsack. And with those 4 things, what I'm going to do is then my base case is when I'm actually going to start at the back of my set of objects and move my way forward. So when n gets down to 0, that means I've now essentially evaluated everything that could be possibly put into the knapsack. Or when my capacity hits 0, meaning like, hey, can't add anything more in it. So those are my base cases. Otherwise, if the weight of the item I am currently considering adding, if that is greater than the current capacity left in the knapsack, then I just recurse and don't select in n, but rather just be like, whoops, can't add this item, it literally won't fit into the backpack, and just move on to check the next thing down. And so you can see all I do with this recursive call here is I don't change capacity, because when I change capacity, that's reflecting me of like having selected putting this item into the knapsack. But I do change n to just be like, just skip this thing, move on to the next one. And then I have to pass along W and V just because I have to along the way. Then our other recursive case, so this is like a, just like don't make a choice, just continue. These recursive cases represent the no, don't select the item in, or yes, do select the item in. So no, don't select the item in. See how that matches this recursive case up here? Make no change to capacity, just move the n along. So that's going to represent our no branch. And then our yes branch is going to combine the current value of this item with whatever the results of a continuing recursion where I do update n, but I also remove the weight of this selected item from my current capacity, and then I continue to recurse. Then I select the maximum value of those 2 branches, and I return those items. So what's going to happen is I'm going to make all of my permutation options, and I'm going to spin up all of these branches of recursive calls. And then as they return back up, I'm going to compare the summation of these items and ultimately finally return the maximum value. So I'm actually not going to reach returning the specific set of items. I'm just returning the total, like what is that maximum value based on the combination of items. I'm going to draw this tree out. I think on this next slide, did I put it over here? Hang on. Refresh. I put a crappy drawing in here. I didn't have a chance to like animate it, but let me walk through this because I think it is interesting. I think it's interesting, so come on the journey with me. So let me move over to the document camera real quick. Oh, wait, sorry. I need to remember our examples before I navigate away. What's going on? There we go. So here, what we're going to do is we're going to start off with a set of items that have a weight of 1, 2, 4, 2, and 5. And then their values are 5, 3, 5, 3, and 2. Okay, there we go. I just needed to copy those things over. Can we do this? Really? That's unhelpful. Hang on. Whoa, I angered it. Maybe this? There we go. Okay. Hang on. Okay. There we go. So here is our recursive code, right? And so what we're going to do is if this is our initial set of inputs, then our initial value, like you can think of these as the indices of the array. They just sort of correspond even though we're storing them in separate arrays. We're going to start our n here. So we're going to say n equals 4 and capacity equals 10, and then I pass along w and v. And the first call I'm going to do is I'm going to call knapsack, and I'm going to pass in the value of 4, and I'm going to pass in the capacity of 10, and then it takes in the other stuff. And then right away what I was going to do is I was going to check, hey, is the item that's at index 4, is its weight, which is 5, does it fit in the knapsack? And the answer is yes. Right now, I can add this item to the knapsack just from a pure capacity comparison. And so I'm going to go into that third case, not my base case, but the second of the recursive cases, the one that has the 2 decisions. And then what you're going to do is you're going to make a recursive call, and one of them sort of represents like, yes, I'm adding the thing in. And so what I pass along then is I pass along knapsack of n minus 1, which is 3. And then I also update my capacity. So originally my capacity was 10. The weight of this item that I am currently considering is 5. So 10 minus 5 is 5. And then my other stuff. And now at this level, the value that I have so far accrued is just this value of 2 right here. So right now my value is 2. My weight left to go is 5. Versus when I make that no call, I'd still call knapsack of 3 because I'm still going to check the next thing, but I don't update the capacity. And so right now, then over here, my value is 0. Now I rinse and repeat. So now my n is 3. I come up over here, I look at 3. I see that weight of this item is 2. 2 is less than 5. So yes, I can possibly add that thing into the knapsack. And so then I would move my n again. My capacity would be 5 minus the weight of the thing I just selected in, which is 2. So that capacity then is 3, blah, blah, blah. And now my value down here is this value 2 plus the value of that item, which is 3. And then I continue. And then I would have a yes call off of this, so on and so forth, until I sort of run out of space. If I come back up and I sort of compare them to the no's, right? Like, so let's say, like I selected that first item in, the permutations come in because each of these yeses have a corresponding no branch. And so this recursive call here will still look at index 2, but it won't have selected in the item at index 3. So I won't update the capacity like I did in this branch. I'm just going to pull that capacity directly down because I didn't include the thing. So the value and the capacity in the no branch stay static, which sort of represents like, skip that item. And then you can imagine like there's a yes branch here. There's a no branch here. There's a yes branch and a no branch. And then you can imagine, right? Yes, no, so on and so forth. So that's sort of what the call tree is generated for a decision problem like this that's sort of selecting 2 possible options and then recursing forward. Does anybody have any questions on how that works? Like how I got this branching tree structure? Yes?
Wouldn't knapsack 2, 3 actually just go like straight down since you can't?
So like what about the yes here? So if I'm gonna try and traverse down this yes pathway, that means I've said yes to the item at index 4, yes to the item at index 3, yes to the item at index 2, and then the item at index 2, right, that has a weight of 4. And so this next yes right here, I think that's the one you're talking about, right? Like my capacity left over is 3. There is actually this branch right here. I'll kind of zoom in so you can see, where what I'm going to check right away is like, hey, is the weight of the thing I'm currently considering exceed my capacity? Then don't bother with that item. So what that's actually going to do is it's sort of like following the yes route, but instead of generating 2 recursive calls off of it, it's actually going to be the like can't fit it. And so it's going to enter this right here. But that still does trigger a knapsack of, like then it would still look at 1. It would still have a capacity of 3. And then we would come up here and we'd say, what's the weight of the thing at index 1? That's 2. Well, look, that item can fit, so if I say yes again over here, then my knapsack is at index 0. I've got 1 left because 3 minus 2 equals 1. And this value here, that value would stay static, which would be 3 from up there. And then this value down here would be, what's the value of the thing at index 1? 3. So this value would be 3 plus 3. Did that answer your question about that piece? Yeah. So yeah, you're right. There's this sort of like middle recursive case that catches those moments when the knapsack just physically can't hold that item. So we try to yes it in, but we're blocked from the yes branch. But you can see, like, it's still kind of like, this is my little branch here. So that doesn't trigger 2, but then I have this yes branch, and this will also trigger a no branch here as well. And I'll keep branching. Yeah. Any other questions about how this works? Yeah. Yeah, eventually, like, we will come down and we'll hit like this base case, right? And so if you think about this as a tree, all the leaves along the bottom of the tree will just be little base cases. And you can think of those as just, like recursive or method iterations that are going to get pushed onto the top of the call stack that just aren't going to continue to recurse. And then we'll pop them all off at the end. So that's how the tree stops at the very end. Last row. Yes. Yes. Yeah. So, and great segue. So, okay. So this is the recursive solution. So let's go back and look at this. So that's the recursive solution. Here, instead, is the memoized dynamic programming optimized solution. But to your point, if you notice, I started N at 4, and then I started to move my way down, right? And so in that case, what I'm going to do is N's going to start at the top. I make my choices. I sort of store them in this extra storage, this like memo. So the difference here is that I do need to take in a new parameter. This parameter, however, I'm going to need to like sort of update its 2-dimensional array. You can also continue to further optimize this by switching the order instead of starting at 5, starting at 0, and kind of building your way up. But the knapsack isn't ordered. When we did from the bottom up in Fibonacci, that was really freaking convenient because Fibonacci has a specific ordering to it where the later numbers are a product of the earlier numbers. There is a bottom up approach to knapsack, but I will admit it's a lot more complicated. It doesn't have quite that nice clarity of it. But I did on the very first slide about this. You see this problem walkthrough video right here? Actually, there's a ton of YouTube videos that walk through the knapsack problem. Like I said, it's super popular, so I'm sure you can find one about the bottom-up approach. But I think this one's probably, in my opinion, one of the like most intuitive videos. So if you're like, Casey, this stupid document camera tree that you doodle doesn't make no sense to me, hopefully this YouTube video will help you out. So let's look through this memoized solution. And just like we saw it before, the memoized solution to Fibonacci, this looks almost identical to the recursive solution, right? So like we can see we have the same sort of parameters, except we added one in. We store this result up here, and we have this extra check. So we only bother to go through our recursive cycle if the thing we're considering has not already been considered. So if that combination has not already been considered, then I go through and look, there's my same base case, my same like I can't fit it case, and my same recursive case, except instead of these being returns, I use the memo to store up the results, and then I return the result. And what's great about that is, remember in that branching tree structure, I now can eliminate any repeated recursive calls by storing any work I've done previously. And so what this then does is, when I had the recursive tree, I had those branches at each level. The first time this goes through, it's going to go from the top all the way down to the bottom, and then it's going to do one branch, but then it's going to eliminate essentially all of the other branches that are just repeated permutations. And so it's going to take this from 2 to the n to ultimately what becomes about 2n separate recursive calls, and the recursive calls themselves run in a constant time. And so we drop the 2, and then our final optimization for this runs in linear time. So that's the answer to the poll everywhere today, is that your final optimized solution can run in linear time. Yeah, question. Oh my gosh, thank you. You're right. There we go. Sorry. This is the memoized solution, as you can see here. So it looks really similar to the recursion, same structure, except I've added this memo parameter here like I did before. I'm checking if it's set before I do any of that expensive work. And instead of returning things, I'm storing the results in memo. Yeah. Questions? Any questions? Like I maybe said to one of the classes, I really think dynamic programming is one of those things that feels very confusing in the beginning, and I can give you language for it, but almost like in the way recursion, you just kind of have to do a bunch of examples, and eventually, like through pattern recognition, it'll become clearer. I really think dynamic programming falls into that category. And so whenever people ask me, how do I prepare for dynamic programming on interviews, they all feel really confusing to me. My honest answer is go watch a bunch of like YouTube video examples, maybe pay for the Leak Code Premium and just go look at the solutions to a bunch of things. And eventually you'll find there's a lot of common patterns like this one, right? Like make an array. Essentially, anytime you would return, just store that item in an array, check if you set that item before you recurse. It's a common dynamic programming pattern. So that's the end of our conversation about dynamic programming. For the rest of lecture, I am going to start a topic that I promised you specifically about what can arguably be the biggest unknown mystery in computer science. That's what we're going to be talking about for the rest of today and Friday. But we did finally finish grading the midterm. Thank you all so much for your patience. This was kind of a weird experiment, so it took the TAs a bunch of extra time to grade it. The grades are now published on Gradescope. And this morning I went through and I took all of your existing Gradescope grades and ported them over to Canvas. I haven't updated them for like late penalties or like those things, but now you can go into Canvas and you can see your like current percentage in the class, so that helps. Here is the statistics for the design review portion of the midterm. Since we had you turn in 2 pieces, what we did was we graded the design creation for just completion. So you just got 5 points for straight up just like submitting a design creation. And then we graded the design review for correctness as a sort of combination of the logic that we saw between the 2 pieces, which is why it took us forever to grade this. And so you can see that right now our median of 45.75 out of 56, that's just for the design review. And that is a median of about 80%, which is honestly really amazing. I'm very impressed, y'all. And then also just add into that score for the 15% bucket that's represented by the midterm, whatever points you earned from the design creation portion. So if you got 45 points on design review and you got 5 points on design creation, your total is 50 out of 61, if that makes sense. Questions about the midterm grades or any of that, how that works? Regrade requests will open tomorrow morning. They'll be open until Wednesday the 1st at midnight so that we have time to get back to your regrade requests. If you have any questions about your grades or you want to chat about it, you're always free to make a post on the Ed board. You can make a post private if you want to just chat about your grades specifically. Any other administrative questions of the moment? We're all just soul crushed from midterm grades coming out. Yeah, fair. I feel you. Cool. Okay. And so I will also say, since we have finished grading and the TAs and I have chatted about it, we've officially decided that your final exam, which will go out on Wednesday the 1st, which is a week from today. Gosh, we're close to the end of the quarter. It's going to be what we're just going to call a take-home exam. So you will have an extended period of time to complete the exam. We're authoring the exam to be what we would think of as 2 hours of in-person writing time, but we're going to give you like multiple days to do it in. And we've decided that if you would like, you may work together in groups up to 3 and submit a single assignment just like you did for your programming projects. Yeah. Any questions about that? Yeah.
Are multiple submissions for the final allowed? Of course, like once you submit it, it's done.
I mean, I think you can just resubmit it until the time comes, but you won't get any feedback on it from submitting it. So, yeah, because it's, you're going to be writing things out and doing stuff like that, and then we'll take it and we have to hand grade it. So, yeah. And just FYI, it'll technically be cumulative. It'll be very design heavy, and it could be on topics from any time before Wednesday the 1st. So technically, the stuff that we talked about this week is also eligible for the exam. Okay. Then, yeah.
Will it involve like typing out answers, or will it be mostly like multiple choice?
It's mostly like typing in English, describing design kind of thing. Yes. Great. Yeah. You are totally allowed to work alone. It is optional groups. Yes. Yeah. But FYI, we will not have office hours. Also, just FYI, we're not having office hours on Monday, Memorial Day. Also, Monday's Memorial Day, y'all. 3-day weekend. And we will not be having office hours anytime after Friday the 3rd. So also a reminder that if you want help on your P4, please come to office hours sooner rather than later, because office hours have still been really quiet and it's making me so suspicious, y'all. But it's okay. I know we all behind. I understand. Okay. Then let's get into it. All right. Let's see. How much time do I want to spend on reductions? Okay. So before I get into the next 2 topics, I will say, FYI, these are pretty theoretical topics. Now, I will admit I teach them in this class because I think they're cool and I'm a big nerd, but like I know that's not a compelling argument for students. So the reason that I also teach you this particular thing is because I think it helps you understand how the run times sort of relate to one another in a bigger context. It also is really helpful to be able to recognize when code is prohibitively inefficient. And I think that that's something that feels very foreign to us in school because we've never asked you to really work at a scale or write a piece of code that is so large that your computer cannot run the code. But what I'm going to be talking about here is stuff that's going to take so long that like no computer in the world or combination of computers together can accomplish these algorithms. But to get there, we're going to talk about something called reductions. And reductions is really just a fancy way of saying how we make connections between one problem and another. So we're about to have a real meta conversation. So remember this thing called topological sort? Topological sort was that graph algorithm where you sort of decided, like, what is the ordering of moving through vertices based on the directed edges. And remember, you can only perform topological sort on a DAG or a directed acyclic graph. So it has to be something where, these are just animations that, fine. It has to be something that doesn't have cycles and does have directed graphs. So that's what topological sort is, just to remind you. Then, I know we've been sort of talking about, I've used the term components. Components is this idea of like stuff in a graph connected to each other. Well, I want to introduce the concept of a strongly connected component. And the definition of strongly connected component is the idea that every pair of vertices in this component is connected via some path in both directions to the other components. So if I look at this graph here, do I have an overlay? You can see D, B, C, D, and E all have a way to get from them to and then back to every other vertex. So this set of 4 vertices is what we would call strongly connected. But unfortunately, A is left out because while A can get to D, there is no edge that goes back to A. So this is a way of us sort of like finding a little subsection of the graph where everybody can kind of navigate within that subsection to one another and back. That's what a strongly connected component is. A is itself a strongly connected component. Now you're like, Casey, why do I care about these ideas? Well, let's say I have a graph that looks like this. Really, graphs are just encoded relationships. That's all it is. So we can use them in a lot of different ways. So let's say I have a graph that looks like this. I can build a new graph overlay that represents the strongly connected components. So here is sort of an identification of the strongly connected components within this graph. So there's 4 separate components, and I can see that there is a way to get from one component to the other. So it's almost like I transformed this collection of vertices into a single vertex and this collection of vertices into a single vertex. And now I've got this kind of simplified graph that overlays this one that I can use to tell me some more information about the graph without having to have quite that level of detail. I, for example, and I wish I had a better example, I do think about this all the time, whereas I think about like, okay, if I'm gonna post something on Insta and I like don't want my mom to see it, like, is she in the strongly connected component of my friends where she will see that stuff? No, that's why I'm gonna post it in my close friends that can't get to my mom and back, right? And so a lot of times you'll find that strongly connected components and this sort of overlay graph are specifically done to find who can connect to whom. So here you can see like A can get to B and B can get to this collection and this collection can get to this collection, but they can't go backwards, right? So it's just sort of giving us an overview, a sort of meta conversation about connectivity. Cool, yes. So it just summarizes reachability, and it will itself be a DAG. That's fine. I just got an email from Sundar. So this lets us collapse our graph into a little bit more of a like high level idea. And so what's really great about this is topological sort can run in linear graph linear time. Determining strongly connected components can also run in graph linear time. And graph linear time is very inexpensive runtime wise. So to process a graph and sort of get this meta conversation about it is actually like pretty efficient. You could think of this as almost free. And so by doing this meta conversation, I can take these graphs and sort of start to figure out how I can relate them to other problems. So I'm trying to figure out how to take a bunch of really specific details about a graph and abstract them away while maintaining the parts that I do need to know, like the connectivity. Like maybe I don't need to know exactly every single vertex, but I want to follow maybe the overall like flow of information, so on and so forth. And doing those calculations runs in a very quick time, which gives me this ability to eventually get to what I'm going to call reductions. Okay. Yes, that's fine. So let's talk about an example problem, and I'm going to introduce this problem as a like input to the thing we're going to talk about on Friday. So let's say Casey is trying to write the final exam. This is hypothetical. We already wrote the final. I'm not actually doing this, but every quarter I teach this, somebody asks if I'm using this to write the final, and the answer is no, unfortunately. Okay. So what I am going to try and do is I want to include your preferences as students into the input for my final exam. And so what if I wanted to collect preferences from each of you as students to determine which topics you want to elect to be on the exam? So I need to sort of express that in terms of computer science, right? Like I can't just be like, tell me your thoughts, and you give me like a laundry list of like English sentences. Instead, what I'm going to do is I'm going to say, you get to submit 2 binary style preferences. You get to tell me one topic you do want to appear on the exam and one topic you do not want to appear on the exam. So for example, maybe you're like, hashing was my jam. I want a hashing problem, but yeah, that like recurrence stuff was nonsense. So no, I don't want recurrences. So those would be like your 2 inputs of opinion to me in this problem. And what I am going to show you is that there exists an algorithm for me to take in 2 preferences from all of you and determine whether or not there is a exam combination that will satisfy at least one of those preferences. So that I can guarantee you're going to give me 2 things. One, I choose this belongs, and one, I choose this doesn't belong. And I'll tell you that at least one of those things will be satisfied. So everybody will get at least one of their preferences officially satisfied with the final design of the exam. You might be like, Casey, what a weird way to frame this problem. This doesn't sound like English. But if you can tell, what I'm doing is I'm trying to take the sort of real world way of like expressing opinions to me and transform it down into binary logic that we can then represent with a graph, and then we can run fancy algorithms on it. So, yes, thanks, past Casey. This, for example, let's say we have Q kinds of questions. Those are like question topics, and we have S students. We could just try every possible combination of options. And hopefully at this point, you've seen from the knapsack, you've seen from Fibonacci, whenever we're sort of doing these types of recursive try everythings, we end up with this 2 to the N, or in this case, 2 to the Q kind of runtime. Because I'm going to try each of your permutations. You have 2 permutations each. And that puts us squarely into what we would call exponential time to just try all the permutations. And gosh darn, isn't that really grossly slow? I've been hammering on about it all week. So instead, we are going to use a graph to represent this. So you can see here is an example of a final exam that only has 4 possible topics. So right now, this exam only represents the topics of big O, recurrence, graphs, and heaps. And each one of these represents one of the possible ways for you to submit your preferences. So everybody gets to pick essentially 2 dots that you like from this set of 8. So maybe you like yes heaps, and you say no graphs would be your 2 submissions. That's fine. So what I can do is I can add in an edge. Each individual edge represents a single submission of preference from students. So right now, what I have is I have 2 students, one, let's see, there we go. One student, for example, here that told me I don't want any graph problems, but yes, I do want a recurrence problem. And I'm going to put an edge between them. There's fine. We made a graph. What do the edges mean? If the edge goes from something making someone unhappy, it's the only thing that can make it. That's fine. So what we'll end up doing is, there we go. We end up with a graph of possibilities and edges between them. And what these little smiley faces are saying is the reason that we sort of put them between your two preferences is because we're going to direct them such that as we move through this graph, we're going to follow these edges and see if we can transform the state from one that satisfies to, or one that doesn't satisfy, to one that satisfies. So once we have this graph of all the possible options and we've got these directed edges, the question is then, are we going to end up having a final pathway through this graph, and the path representing the selected vertices, and the vertices then showing us what things must be true about the exam in order to satisfy everybody? And in fact, you can just run the strongly connected components on the graph, because the strongly connected components would satisfy a bunch of people, for example. So here's a graph of a bunch of things. I can see here that we've got a bunch of graphs that satisfy people. And then we can run topological sort on the items. And eventually I will get a list of all of the possibilities of whether or not I can make a graph, and specifically the pathway, including all of the variables that I would use to make the graph or make the exam. I know I'm clicking through this really fast, and I know this sounds like really dense logic, but I'm just giving you an example of how we go from like complicated real world problems to this like combination of like, okay, maybe I like abstract into strongly connected components and I sort of represent this in a graph, and et cetera, et cetera. And also part of this is like really foreign because this idea of satisfaction is actually a huge topic in computer science. And 2SAT, which is this problem that we just went through, is a canonical example of a computer science problem that we could kind of apply to anything, right? So I just talked through about how we might do this with an exam creation, but you could do the same sort of process where you take in two preferences from everybody, you make vertices that represent the preferences, you find the strongly connected components, and then you find a topological sort that moves through the strongly connected components, and that will give you a way to take in sets of two pieces of logic or preferences and finds you a final solution or state that satisfies those two choices. And because I mentioned finding strongly connected components and finding topological sort, those are both graph linear problems. We just went from the 2 to the q, that exponential runtime, down to graph linear runtime, just like we've been doing with dynamic programming. And the reason this is so exciting is because, like I said, this is an example of what we call the 2SAT problem. Given a set of Boolean variables and a list of requirements, each of the form variable 1, true or false, variable 2, true or false. So you can imagine in the final exam example, this would be like, yes, include graphs, true. No, don't include heaps, false, something like that. We can set that to really, gosh darn, any scenario, can't we? And so, if we can abstract away anything into a 2SAT problem, hopefully I just showed you that you can solve the 2SAT problem in a graph linear time, which means anything you can adapt into this kind of 2SAT situation does have what we will call a efficient solution, has a graph linear solution, which means that you can put it into a computer and get an answer out. That is not true of our previous runtime of 2 to the q. And so what we've got now is we've got a sort of like logical representation of how to find some way of satisfying two sets of two variables that we know a computer can solve, which is really exciting because what we've done is we've reduced the final exam problem into this 2SAT. And I can just tell you, because I just showed you, 2SAT has efficient solutions. So you could run this on a bunch of different algorithms. Here's the foreshadowing that I will give you for Friday. Now that we have like found a way to sort of translate problems. What we can do is we can take a problem, translate it into 2SAT, run the topo sort, run the strongly connected components on it in graph linear time, and then do some translation back. We can solve a lot more problems. It's like we've sort of found almost like a secret key for problems. As long as we can translate them into 2SAT, we know we can solve them, right? It's like a little special tool. Well, fine, reductions. You can apply that, for example, to this thing called 2-coloring. This is another problem that can be solved with the exact same solution. And the problem is just, can you find a coloring where you always oscillate back and forth? And I can promise you that that 2SAT thing, this can be translated into 2SAT and it can be solved. Now, here is my question to the group. What if instead of doing 2 possible Booleans, I gave everybody 3 Booleans? Do you think there exists an efficient solution to 3SAT? If there exists an efficient solution to 2SAT, does there exist an efficient solution to 3SAT? And if you know how to solve 2SAT, can you figure out how to solve 3SAT? I will leave you with those open questions. Come back on Friday, and I will show you the power of this weird logical representation and possibly helping us solve every problem we've ever figured out how to tell computers. Thanks so much, everybody. See you Friday.